Hello everybody. Today's topic is diagonalization. To start with, we want to recall how to find eigenvalues and eigenspaces. So for a given matrix A, squared matrix n by n, the first step is to find eigenvalues by solving so-called characteristic equation given by determinant of A minus lambda I equals 0. And you want to write it in descending order from the largest to the smallest. The second step is to find corresponding eigenspace. By corresponding, we mean for each lambda I. So first you start with lambda 1, right? So for lambda 1, find eigenspace of lambda 1 by looking at null space of A minus lambda 1I. And then turn to lambda 2 and you solve eigenspace of lambda 2 by looking at null space of A minus lambda 2I. All right, and so on. Now, we're going to first introduce the definition of similarity and diagonalizability. So, similarity is kind of a relation between two squared matrices. So suppose you are given two matrices, squared matrices A and B, and we call A is similar to B, we denote it by A wave B. If there exists some invertible matrix P such that A equals P, B, P inverse holds. So this is the relationship between A and B. It is very often we can consider this as if you multiply by P both sides on the right hand side, right multiplication, then you get AP equals PB. So in many cases, instead of considering the definition A equals PB P inverse, it's better to consider AP equals PB as a substitution of this definition. Now, a square matrix A is called diagonalizable if A is similar to B, where B is diagonal matrix. So a diagonalizable matrix A is good matrix. In what sense? Because if one is diagonalizable, then the power of this matrix, diagonalizable matrix, can be reduced to simple calculation. So for example, if you look at A, if A is diagonalizable, then it can be written as P, B, P inverse, right? So suppose we think of 3 by 3 matrix. Then P and the B is diagonal. So lambda 1, lambda 2, lambda 3. Others are just 0 and P inverse. This is definition of diagonalizability. And A squared, if you write P, B, P inverse twice, then P inverse P in between, they're canceled each other. So we have P, B squared P inverse. And it is easier to compute power of diagonal matrix. So this is just squared of diagonal entries. If we have K equals 100, A to the 100th power, then P, B, K, P inverse, this similar cancellation will apply. And then we have P, lambda 1K, lambda 2K, lambda 3K, P inverse. This is much easier than just multiplying A 100 times. So diagonalizable matrix is good, but not every matrix, every square matrix is diagonalizable. So we want to answer what kind of matrix is good or is diagonalizable. So to do that, here's partial answer. Suppose m by n matrix A is diagonalizable if and only if A has n many linear independent eigenvectors. So this is necessary and sufficient condition. In other words, to prove that we should show both ways, both directions. First direction, let's come back. So if A has n linear independent eigenvectors, so we can list them, name it P1, P2, Pn, n many eigenvectors. Then of course for P1, by definition, it satisfies P1 equals lambda 1 P1. So there's some number eigenvalue corresponding to P1, right? So we call that as lambda 1. And all the way down to the last one, so it corresponds to some other eigenvalues. And we know that AP1, this is a matrix, this is vector, column vector. So each one here is column vector, is equals column vector. If we put them together side by side, so we can put it as in one bracket. So that gives me a matrix on left hand side. And then we do the same thing, but we put corresponding right hand side. Okay. All right. Now from left hand side, we can take out A and P1, P2, Pn. From right hand side, we can rearrange that as P1, P2, Pn, and multiply by lambda 1, lambda 2, and lambda n. All right. Now we set or denote P1, P2, Pn. So because P1 is vector, P2 is column vector, and Pn is another column vector, so it's a m by m matrix, we call this as P. And we call this as the matrix D, diagonal matrix. Then we have AP equals, so coming back here, A times P equals, this is P, right? So we have P times D. Now, if we move P to the other side, which means we need to multiply P inverse, which is right multiply P inverse both sides, then this is A P P inverse equals P D P inverse, and this is I, so we get A equals P D P inverse. Here we implicitly used linearly independence condition to produce P inverse. So linearly independent M eigenvectors, put them together, it come up with the invertible matrix, which is from inverse matrix theory. All right, I'm going to leave the other direction to your own exercise. Now, we look at another proposition which is more practical. So if A has n distinct eigenvalues, we know that m by m matrix, it has at most n many eigenvalues. At most, but it's not guaranteed. Sometimes one, sometimes two. At most n distinct eigenvalues. So if A has n distinct eigenvalues, then we say we can conclude A is diagonalizable. But this thing is conclusion of the first claim. So if A has n distinct eigenvalues, then eigenvectors of A are independent to each other. And from previous proposition, suppose you have n many linearly independent eigenvectors, then it is diagonalizable. So 2 is corollary of 1. So 2 follows from 1 by previous proposition. Now we look at, so it's enough to prove eigenvectors are independent. That's the first claim. So to make it simple, we are going to look at n equals 3. And suppose A is given by, so 3 distinct eigenvalues. So we have A P1 equals lambda 1 P1, A P2 equals lambda 2 P2, A P3 equals lambda 3 P3, right? And we also have lambda 1 is not equals lambda 2 is not equal lambda 3, and these two is not, lambda 1 and lambda 3 is not equal to each other. So from here, what I want is, I want P1, P2, P3 is independent. So let's look at if P1, P2 are dependent or not. So question, is P1, P2 independent? That's easier question than compared to the independence of 3 vectors. So the proof is this. The solution. So if P1, P2 dependent, then P1 is scalar multiplication of P2. Then we can write P1, or P2 is scalar multiplication of P1 for some K in R. This was proved in one of our homework, I guess. And then we have this and this relation. Try to find contradiction. So I put this down, copy paste. But instead of AP2, I will write AKP1 equals lambda 2 P2 is lambda 2 KP1. Of course, this is reduced to, because K is non-zero. So K can be cancelled each other. So AP1 equals lambda 2 P1, which is contradiction. So we have AP1 equals lambda 2 P1, AP1 equals lambda 1 P1. In other words, lambda 1 has to be lambda 2, which is contradiction to our assumption, all distinct eigenvalues. So P1, P2, independent. Now let's go back to our original question. So if you look at 3 vectors together, can we prove, so prove P1, P2, P3 independent? So the proof is following. We're going to use the original proof, but first, if not, in other words, P1, P2, P3 are dependent, then we write P1, C1 plus C2, P2 plus C3, P3 equals 0. For non-zero C1, C2, C3s, right? This is, so, dependency. Now we get this and try to cook up a contradiction. So what we do is we apply A both sides. So A times the whole thing, A times 0, which means we have C1 AP1 plus C2 AP2 plus C3 AP3 equals A times 0 is 0. Now, because AP1 is lambda 1 P1, we just write whatever it is given from eigenstructure. So we try to make contradiction to these things. So we have this equation and we have this equation. We try to make some contradiction between these two. So what I do is, let me say this is 1, this is equation 2. So what we do is, I'm going to reduce this problem. So 1 times lambda 3. So both for each term of 1, we multiply by lambda 3. Lambda 3 is a number. And then subtract to equation 2. So what it means is 1 times lambda 3 is C1 lambda 1 P1, C2 lambda 1 P2, and C3, multiplied by lambda 3, right? So we have C3 lambda 3 P3 equals 0. This is 1 times lambda 3. And then subtract these two, so we get, of course these two will be cancelled. That's why we multiply by lambda 3, but other things are not cancelling immediately. So C1 P1, but here lambda 1 minus lambda 3 plus C2 P2, but we have lambda 2 minus lambda 3 equals 0. But from previous argument, is P1, P2 independent? The answer is yes, right? We proved that here. P1, P2 should be independent. What does it mean? It means P1, P2 independent. It means those weight in front of this must be 0. But we know lambda 1, lambda 3 are not equal to each other, so it's not equal 0. Similarly, it's not equal 0. The only possibility is C1 has to be equal to C2 and equal to 0. Otherwise, these two are dependent, which is contradiction. So we concluded, if this is, from this assumption, C1 equals C2. And similarly, we can prove that. So that means number 1 is reduced to C3 P3 equals 0. And we know that by dependency of P1, P2, P3, you cannot have all C1, C2, C3 equal 0 at the same time. So C3 is not equal 0. And P3 as eigenvector is not equal 0. But this guy, right hand side, is equal 0. So that means it's a contradiction. So this is not equal 0 and equal to 0, which is contradiction. All right, I'm going to end this video here, and then we continue in other video, some examples with calculations.